And there is an option joint rooms.
Good afternoon, Ruby, Dylan, Ryan, Jensen, Prashanadu. Anyone? Can you please tell me whether the breakout room from yesterday
we can enter breakout rooms ourselves, and I think
are still there or not?
Yeah, we still have our breakout rooms.
And still access. Good. Okay, then we don't need to have a new one. Huh? Thank you, Zhang.
But for me, I can't say.
Yeah, pronounce the name correctly, Zhang. Zhang or Zhang? Kavin, yeah. Or Wihan?
It's Jean, sir.
Or under charts?
Yes, Dr. Tay, so I can't see my breakout room as well.
I don't know. Maybe some of you are not assigned yet, you know. Oh, sorry. I just switch on my speaker. Maybe you say something to me already just now. And please don't write those things in the room, you know, because every time you write, we will hear this sound, you know, yesterday, too much. Please stop writing there. Again, may I ask, Zhang, did I pronounce your name correctly? Wihan, Zhang or Zhang?
Jean.
Zhang, huh? Okay. Thank you. Yeah, just now I have my speaker off. Fortunately, I realized that. Okay, 4 p.m. Yeah, good afternoon. Okay, so today we start with a little bit of things. Yesterday, remember, some student asked me this question. Yeah, that's why I don't write in this room again, please. Yeah, okay, because you give this response. And based on your response for the Q&A meetings, I will make a little bit adjustment for the time. Okay, looks like students like the 2 p.m. class, so I will make a little bit of adjustment, and you can check the announcement table for next week later, maybe by the weekend. Okay, I will tell you. Okay, and this is something very interesting to start begin with. Okay, yesterday some student asked me a question like this: why don't we let's see. Okay, yesterday we talk about a number like 183. A student asked me, why don't you approximate this to 185, you know? So I have an idea, maybe this is what is happening. Okay, now look, as I said, in different culture, maybe we have different rules, you know? So my guess is this. In some culture, maybe this is the way you do things. And this is interesting, you know, about human behavior. 185, 180, 185, 190, okay, 195. So this is our range. Now, it might happen that in some country, people like to do things this way. From 182.5 to 187.5, they will round it off to 185. This is what happens here, no? 185. And for anything here between here, 187.5 to 192.5, then they are going to round it off to 190. No? Similarly, between here, then we round off to 180. This is maybe what is happening, you know, for the student who asked me yesterday. For for the system we use, we round it 183 to 180 instead. And this system actually will follow the British system, the Cambridge A-level standard. Okay, and this is what we do also in Malaysia. 0 to 10, then to 20. But for this system here, maybe you like this, 0 to 5 to 10. Okay? And this is an interesting aspect, I think, because it shows the human behavior, beside the way we think. For example, if you look at our clock, this is 12, This is base 10. We are used to base 10 system, but this is 12. But 12 is a nice number. It can be divided by 2, 3, 4, 6, and so on. So if we have 12 fingers, we might choose 12. Unfortunately, we have 10 only, right? Then you notice that this is actually happening everywhere in our world also. For example, when your smartphone and also your tablet, your computer screen, whenever you purchase them, you find that when you want to look for the size of the screen, sometimes when it is reported in millimeter, it will be a strange number, like 283 millimeter, right? Strange number. However, if you convert it to inch, you will get a nice number, 12 inch, 18 inch, 24 inch. Okay? Therefore, actually, we are using the standard of the inch, not the old standard 12 inch. Then you can ask, what happens? Why do we want to use inch instead of using meter or centimeter? The reason is that the superpower set the standard. Who are the superpowers? Now we know this is the United States. Okay? And if you observe in the world, there is one strange thing. If you go to the supermarket of the countries, in Malaysia, if you want to buy something, we use kilogram. Things are measured in kilograms, the weight, okay? However, if you go to the United States and I believe UK, if you go to the supermarket and purchase, for example, orange, apples, the thing will be given in terms of pounds. Now, 1 pound equals 16 ounces, still in pounds, okay? And also in a lot of standard, the industrial standard, all the machine, the cutting machine, everything is in inch. They are calibrated in inch. Then, because it takes so much money to change all these things, therefore people tend to stick to that, and the superpower wins. There is no say from others. We just follow the superpower. Okay? And what else? And this is what I want to tell you. This kind of rules humans set to tidy up the thing, to make the thing look nice in our world. Okay, we need rules. And there was something like in the rooms, when you are chatting, you have to be polite, okay? Don't write something that hurt others or that others might look like an insult. Don't do that, okay? This is a rule to stay in a world in harmony. And also for these random errors, the errors we did in the past few weeks, uncertainties, we have some rules, right? Remember, I said that the uncertainty, usually we report in 1 significant figures. We want to round it off to 1 significant figures. This is a rule. But in some very special circumstances, we might not want to follow this. The reason is in one of the exercise. I think you get something like, I think it is this one. If you have done that, okay, you get a number like this if you round it off to 1 significant figures. Okay, now let us observe this. If you do this, this means the uncertainty, the percentage uncertainty is very huge. Right? 2/5, this is about 40%. Very huge uncertainty. Therefore, sometimes, if when the uncertainty is so large already, we don't want to keep 1 SF, 1 significant figures. We might want to keep 2 significant figures. For example, I don't remember the exact number. For example, let's say this. Maybe we want to keep this instead of this one significant figures. This is 2 significant figures. Why? Because the errors is already so large. We don't want to lose more, by rounding it off to 1 significant figures. So in this case, very special one, we want to keep 2 significant figures because we want to keep the precision here. We don't want to lose more precision. So in this kind of circumstances, maybe we want to do this. Okay, so naturally students will be very worried about what should you do in the exam. So here's my word again. In the exam, I will tell you how many significant figures you should give in your final answer. Okay, that is the exam. I think you should worry more about the real life. In our actual life, which one you want to choose, you need to do that with wisdom. Okay, you need to evaluate the situation and think about which one to use, and that to bring up, present the thing nicely. Is it okay?
Yes, sir. Yes, sir.
Okay, so please understand, don't memorize the thing. And also, I realize many students ask me, they still have not yet learned to distinguish between absolute uncertainty and fractional uncertainty. They are different quantities. Okay, this one has no unit. No unit. This one has a unit. They are different quantities. And so when you write your equation, you need to be careful, be aware which one you are talking about. Are you using fractional or are you using absolute uncertainty? Do the thing step by step. Okay, so that's it. I hope you not fall asleep. This is so hot today. Okay, now let us start our class today. New chapters. We will not go through each of the question in tutorial because you can ask. Come to us, right? I saw some of you already asking the tutor. Okay, so let us start with this. Chapter number 3, analyzing data. Actually, what we have been doing in chapter 1, chapter 2, they are all leads to this one. Our purpose is to analyze the data. Right? So this is the main thing. So what we want to do today in this class, in this chapter, is to record the data. This one we already learned. Record the data correctly in the tables with uncertainties. And then the most important thing, we want to plot the graphs. Plot graphs, learn how to plot the graphs. Why graphs? Because we can analyze the graph using straight line, best fit. So we want to turn the graph into a straight line graph. And then we can analyze the intercept, the gradient, and get information from this. And this is the most important thing, what we have to do in this chapter. Okay, so first, let's start with recording data. So we use a table to arrange things nicely, a table. And these are the things that you should have in your tables. The title, of course, a title. The first thing, titles. Then for each of the things in the data in the tables, you should have the names, proper names, and then symbols. Okay, symbol is an abstraction of the names. When you do the exercise, you will find that we don't deal with names anymore. We deal with symbols. This is mathematics. We abstract the thing. Then we just deal with symbols. You play around with symbols to get the final answer. And this process is mathematics. You don't need to think. You think about how to manipulate the mathematics, but we don't need to think about the meaning of each of the concepts anymore. Once you write down the equation, whatever follows is just mathematics. Computer can also do that. Okay? And this is the power of mathematics and power of abstraction. Then units. Many students up to this point, many. Usually you do something without units. Be careful, this one, you should really correct this. You must have a unit, and now a new thing, uncertainties. Okay? So for this chapter, the best thing now is to discuss, is to introduce an actual lab experiment. Then we will go through step by step, okay, all the elements, how we can start recording, then do the graph, everything, finally get some information. Okay, so the thing we want to look at is the simplest thing. We have given a spring. A spring has a spring constant K, and this is the thing we want to determine from our experiment. Okay, how? Using mass. We know if you attach a mass to the end, and then you can set this into motion, the thing will start to oscillate, right? And when you change the mass, you find that the period is one complete oscillation, the time taken for one complete oscillation. We also change accordingly, according to the M, to the mass. So when you change the mass, you get different period. Using this relationship, this is the thing we can measure. Use this, we can then analyze the data to get K. Then we'll see how we can do this. So let us start our measurement. You change the mass, you get some standard mass like 10 grams, 20 grams. You put it at the end here, and then you measure the period. But the period is too short. This will give us a lot of errors. So we instead measure 20 periods. Then 20 oscillations. Then we record this. This is the raw data, the preliminary data in a table like this. So you notice a title, mass versus time of oscillations. Then for each of the thing, you have the mass, the names, the symbols, and then units, uncertainty. Okay, the name for 2 oscillations, 20 oscillations, the symbol, the unit, the uncertainties. Okay, so then you change the mass, 20 gram, what is 12? What is the 20 oscillations? You record this down. So here, this plus minus 1, I chose it arbitrarily. Usually in the standard mass 10, 20, 30, we are not given the uncertainties. So we just choose 1 gram. I think this is something reasonable. And for this time here, I choose 1 because the human reaction, remember, is 0.2, right? Actually, this is too short a time. So I just pick 1 second. Okay. Now, it is very hard to be really precise when you have seen this thing not go up and down, up and down. Very difficult to get 0.2 seconds. Okay, so this is the first raw data. Then we want to analyze. So we need some theory to model this from our understanding. And here it is. Okay, so this is what we have been talking about. And then we know the period and the mass is related by a relationship like this. The 3 quantities. So divided by k, this is square root. Okay, they are related by this. Then how can we extract information using this equation? Apply this data to get this. And many of you have learned this. So you need to realize, right, from this equation, k here we assume this is a constant. And this k is a constant. So t and m, they are variables. Therefore, if you plot this graph, t is a square root m, right? So you can think of a graph like this. X. So you know, if you plot a graph like this, you get something like this. Y against square root x. You get a curve. X. If you plot y against x directly from here, you will get something like this, a curve. A curve, we cannot do much with a curve. So what we want is we want to draw a linear graph, a linear one. We want to convert this equation to plot it in such a way that we get a linear graph. Okay, so how? You just plot it against square root m. Okay, from here, square root m. Okay, so if you plot this with square root n, we are going to get a straight line. Okay, now you have something like this. This is square root m. Just now, previous slide, we used m only. T, right? So we expect this should be a straight line passing through the 0. Ideally, this is what it should happen. This is what we want, straight line. We call this a linear graph with a best fit later. Okay, so this is the first thing you need to determine. What kind of quantity you want to plot, you want to choose, you want to plot. Choose it in such a way that this is a linear graph. Because a linear graph, we can calculate the gradient easily, the gradient. You can calculate the gradient. And we can do the best fit. Then next, so now let us find out. We need the period and the mass. Then we know the period is related to the 20 oscillations like this. Now the time we measured just now divided by 20, you get the period. So you can calculate this number. Okay, then the next question, what is the uncertainties in the period? Anyone? You have learned this, right? What is the uncertainties in the period?
One second.
1 second. Let me see. Is that right? How do you calculate this? From yesterday, we learned. How do you calculate? Do you know the uncertainty in the T?
Yes, so it's 1 second and then divided by 20. So it's actually 0.05.
Yes, good. Okay. This is what we learned. Because we take 20 as a constant, you get this equation. This is what we learned. Okay. Then what is delta T? Is the uncertainty. We record it down there. Remember here, we choose 1 second here. This is the delta small letter t, 1 second. You divide it, then you get 0.05 seconds. Okay. Now the question is, is it the same for all the data? Is it the same for all the different mass for the different time? This quantity, these errors, are they the same or not the same? There are 5 lines here, right? Five data here, 5. Should you use the same 0.05 for all of them? Or are they not the same? Anyone? Yes?
Well, they shouldn't use 0.05.
The same, huh? Okay, the same. Okay, you should use the same thing for all of them. And now we complete T period. Now we go to square root n. Now this is interesting. We learned yesterday, right? Square root of n meaning power half. Okay, do you remember how can you calculate the uncertainty for y in this way? Recall the formula. How? For power, what should you do? You bring down the power, remember? For power, you should use the fractional uncertainty, fractional. Meaning, this is the fractional in y, right? You have only one variable m. So what you should do is, the fractional in m will give us a contribution. This is the only contribution. Then this power here, you bring it down here, half. Okay, if this is a whole number, you bring down the whole number, and we have only one quantity. And many students, I found that they do things without this y. They just write it this way. And look, if you look at this, delta m over m, what is the unit of this? What is the unit?
No unit.
No unit, sir.
No unit. What about this? What is there a unit? Yes.
No.
Yes, there's a unit.
Yes, right. So is it correct? You learn about this in your mechanics, right? The first chapter, dimensions. The left has a dimension, the right has no dimension. So this is a wrong equation. You should have divided by y. Then this is the correct one. Dimensionless, dimensionless. Okay. So this is a very useful way to identify the error in your equation. Now look at the things nicely. Then you write it nicely. Then you can find out your errors immediately, almost immediately. Okay, that's it. And now let us calculate. If you want to calculate delta y, the uncertainty is square root n. What should you do? You want to get rid of y, right? Get rid of y. So what is y? Y is square root n. So let us multiply square root n on both sides. Okay, multiply. Then y is just square root n. This is what we want. It cancels out. You are left with this on the right hand side. Then this you can power, right? This is n half. This is n1, right? Half minus 1, you get square root n. Below there, below. This one's already below. Okay? This is how you identify this. Now we have this formula. Okay? So let us now calculate. There are 5 masses, right? 5 different mass. 20, the first one is 20. The uncertainty in mass is 1 gram, right? So we can calculate, get a number. For the first one, you get this, right? 20 grams, delta n is 1 gram, and you get this number, 0.112. Okay? Sometimes, let's say if this is a final answer, as you say, we run it out to 0.1, and this is the unit. However, here, this is the exception. You run it off only for the final answer. But here is just intermediate. We are not yet at the final step yet. So let us keep a few more. Okay? Keep a few more. Otherwise, there might be runoff error. Some of you have done that already. Okay? So don't just apply the rules everywhere. You have to consider the situation. Now this is the intermediate only. We are not yet at the final stage. Intermediate. So keep a few more. And how many more? We will see later. This is your experience. Okay, I hope this is clear to you. And compare this. This is the first one, right? 20 grams. Then you have followed by 50 grams. Then is it the same? When you apply this formula to 50 grams, you get the same number, 0.112. Already say here actually, right? It's not constant because m varies. You can see here. Delta m from the table is always 1 gram. But you have different m, right? Different mass, 20 grams, 50 grams, 100 grams, 120 grams. Therefore, the uncertainty for each of them will be different. So you must calculate each one differently. Okay? So be careful. Sometimes uncertainties is different. Sometimes they are the same, depending on the situation. Okay, so you calculate one by one, and you put them into a table like this. So see, this is just a copy of the previous table. Now we have 2 new columns. This is what we want. Right? Square root of mass, you put the unit, period. Now we have the period, and this is the same, plus minus 0.05 seconds. If they are the same for all of them, we just write it here. For this one, a little bit more complicated. They are all different. So I write it this way, plus minus, everyone, you put it there. So my question just now, how many significance figures should you keep for this 0.11? Just now, what do we get? We get 112, right? Can you see the reason behind this? Why do I do it this way? You compare. Why do I keep 2 significant figures for the first one and then like this? Can you see the reason behind? Does it make sense to you?
This will be more precise.
Okay. There is one thing. The reason is here. Look, because all the other, the last 4, they start from the second decimal, 4. Okay. So now let's say we want to use our rule. This means we keep 1 significant figure here, and then we keep 1 significant figure. Then we end up with 0.1. You can see what happens. It looks very strange in our equation, in our data. This one you don't have, because you insist, right? I want 1 significant figure, you get 0.1. Then this becomes 4.5. And the thing looks a little bit incompatible, you know. This is 2 decimal. Then the first one is 1 decimal, 1 decimal. It looks very strange when you plot. Because when you plot it on the same scale. Remember, the graph has a scale, right? You plot it on the same scale, but one of these you have a small scale, a small one, but the other one has a bigger one. Therefore, they are not compatible. Okay, so that is the reason I keep here the first one 2 significant figures, and of course to be more precise. If you want, sometimes you can keep one more here, one more, like 0, 1, something like that. Keep one more if there is a reason to do that. But you can see already, this is 0.077. It is about 1%. It's so small already. So there is no need to keep one more. And there again, it's not definite. It depends on the situation. Okay? Then we have this. And then we point out one by one. Look, the title of the table. Those are the things you need. The name, the symbol, the uncertainty, the unit, everything. Name, symbol, uncertainty also here. And then the uncertainty of the derived quantity, you should write it down here. And the last one is here. You want to round off the average value. This value according to the decimal place of your uncertainty. Here, period is simple. The uncertainty is at the second decimal, right? So here, everything you should keep to the second decimal. Okay, we have been talking about this all the time. Here, also second decimal, right? So you keep this. round it off to second decimal. Then our data looks really tidy. And when you plot, it will also be simple, very convenient to plot. Okay, any question up to this point?
No questions, sir.
No question, right? But then I want to remind you, okay, here is really the full scale data analysis, full scale. We do all these things. But in your, there are 3 physics class in your this semester, right? Mechanics, matter, and also electricity and magnetism. You need to do a lab for these 3 things. And for the other lecturer, mechanics and electricity, magnetism, they may not ask you to do this uncertainty. They may not ask you, so you don't have to apply this everywhere. But for us, we will do this for only one of the lab, the second lab. The first one, we will do a labor calculation. Okay. The reason is this is very tedious, a tedious process. You need to do a lot of things, as I will show you later. You need to plot the error graph, everything. If you do that by hand, just one graph takes a lot of time. Okay. So remember this, the other class, you might not be asked to do this, but we will do that in one of the full-scale graph, in one of the lab only. Okay, and also you some exercise, 2 of them, but some of them I will not ask you to do that. Okay, so here, this is the first part, data. We have calculated all the data. Now we move on to the second part, graphs. So we want to analyze our data, the results, we graph. Usually this is what we do. X-axis, y-axis. Remember in mathematics, you learn something like this. Y equals fx. Let me write down. You do this. Y equals fx, right? Y is a function of x. So when you plot the thing, you are changing x. You assume x is changing. And a changing, let's say you start from x here, give you this number. This is your y. Fx, y. When you change x to a different number, you get another number. Let's say this is x1, x2. You get y1, y2. Okay? So you change x, you get y. This means this is an independent variable x. They are independent. We change it. And the one that depends on this, y depends on x. Y depends on x. Y is the dependent variable. So usually we do the thing this way. This again is the standard. This is how we are trained to think. Like this. So you can think actually a function is like a factory, a machine. And this is your machine. Okay, your machine. A black box, for example. Here there is a hole. You throw in some raw material, X. You throw in material X. Then the machine, you call it F. And then you come up with the product Fx. You call this Y. Okay? This is actually a very nice way to think about the idea of function. You should have all this, have this thing in your mind. F is a machine. It add on X. This is a raw material, produces the result Y. Okay, you should have this idea, function. It's an important idea. Okay, functions. Then you can plot a graph here. This is the function graph. Every x gives you a y. Now, what is a good graph? What elements should be on a graph to be called a good graph? Here, again, title. Always title. Then you have the 2 axes, right? You should have the label for your axis, and then units. You must have units. Otherwise, we don't know what you are talking about. Okay? Label, units. And important, axis need not start from the origin. Students have the wrong idea. Always the axis must start from 0. No, you don't need that. It's not needed. And also, if you don't start with the origin, then some students like to do this. They do this. Do this. This simple, no? Do this. Is it necessary? Whether you like this or not is up to you. but I don't like this. Looks ugly. We don't want to have some zigzag here. I say again, this is not a standard, but I just don't like this. If you like this, you can put it. I wouldn't penalize you, but I don't like this. You don't need this. It's unnecessary. The reason is when you plot the thing, you have to write the mark here very clearly. Let's say 5. This should be 2. This is sufficient. We know it starts from 2, not the origin. Those with the eye can see that it themselves, unless you want to emphasize it, but not needed. It is wasted. This part is wasted. Okay, so understand this again is not a stand, it's a rule. Sorry, what is it? A preference. Okay, don't argue on this. Now, next one. Choose a good scale. You must choose the scale to cover the whole range of your y and x. Remember, just now we have this y, x, right? You have y1, y2, everything, x1, x2. So you have a range, x from the largest, smallest, y largest, smallest. So you must fit all this range within your graph. Let's say this is your graph paper. Okay? So you want to choose a nice scale, x, y, right? To fit almost all of them, all of your graph. More than 80%, I would say. This again is not a standard. This again depends on how you choose. By experience, cover as much as possible. You don't want something like this. And then some students like to do things this way. They draw a small graph here. I don't know why. They like this mini. What is it? Mini. Forget in architecture. There's a mini thing. I forget the name. Minuscule thing. We don't like this. We want a big one. The reason is when you have a big scale, the error is small. Small error, right? Of course, if you have something like this, this is 0 to 1 centimeter compared to something like this, 0 to 1 centimeter. Which one is more precise? Of course, this one. When you are calculating the gradient, this will give you a better precision. Not this. We don't want this. Okay? Not this. We want this. Okay. Next thing is choose something nice. Have you ever seen someone do this? Choose. Let me see. Choose 1. Choose 1, 3, 5. Yeah. Does it look strange? Does it look nice to you? 1, 3, 5. You have something like this. As I said, right? We have 10 fingers. 10. So best 10. We want to choose things that we can divide 10. They can divide 10 precisely. 1, 2, 5. Yeah. This is the thing we can divide 10 precisely. That's why you choose something like this. Sometimes maybe you can choose 0.25, right? 2.5. Maybe there is one possibility. But don't choose something like this. Don't choose a strange thing. For example, 3.1, 3.3. I don't know. Very strange. The reason is if you choose this number 3, when you divide something, most of the time you get a number like this, 3, 3, 3, 3, 3, 3, 3, 3, 3. Very hard, very difficult to deal with. Now you have to throw them away, and then that causes round off errors again. So we don't want this kind of thing. We don't want this. Remember, we don't want this kind of strange thing. We want something like this, nice thing. Okay, choose a scale like this, multiples of 1, 2, 5, and so on. Something you are easy to work with. And you can plot a nice graph with this. Okay. Next thing is you plot the point, right? X1, Y1 give you a point. X2, Y2 give you another point. We want to choose. Students always do things this way. They choose this. Never mind, use red. Okay. Students sometimes choose this dot. Now let me ask you. You plot the graph with a dot like this. This is x1, x2. Now compare this with a cross. Which one do you think is more precise? X1, Y2. Now look, you draw this thing. This is not a perfect square sphere, right? then you need to identify the center of this thing. That is the precise point, but this is difficult. But if you draw a cross, and you draw a cross, then immediately, excuse me, yeah, if you draw a cross, immediately you know the precise point is here, the center. This is the precise point. That's why using a cross is very precise compared to a dot like this, a big dot. If you put a small dot, you say precise, yeah, sure, I agree. But it is very difficult to identify in your graph. Okay, this is why, for this reason, usually I choose crosses instead of the dot, big dot, or small dot. Again, this is something that we will not argue about. This is again not something definite. This is just a preference, and there is a reason behind this preference. Okay, the last thing is error bars. Now, error bars will show us the errors, the uncertainty, and this is a new thing to you. Now we will do this afterwards. Okay, there is something else. Here I just show you first. This is how a graph will look like. A title. Okay, a title, axis label, units, and then the plot point, right? A cross. Then you need to plot a base fit line. T versus square root m, you give you a base fit line. So how do you draw this base fit line? If you use a computer program, it can give you this immediately. But if you don't have a computer program, then these are the rules we need to plot a good one, a straight line graph. How do you decide that? This line, the base fit one, should have the following properties. You need to remember, it does not need to pass through every point, not needed. It does not need to pass through the end point. It does not need to pass through the origin, because there is nothing special about the end point. There are 5 points. One has to be the end, one has to be the beginning. No special meaning has to be attached to these 2 points. So you don't need to pay special attention to that. What you want is to look at all the points and plot the base graph. Also, origin, sometimes you don't need it because of the errors. If you have a 0 errors, your thing will not pass through the origin. If you force your graph to pass through origin, that will result in more errors. Okay? Without passing through the origin can help us to estimate the error, the 0 error. Okay? So this is the thing. Second, you balance the points on either side of the thing. And if there are some anomalous point, some strange point that is jumping, that is far away from others, then you should either check it if it is possible. Now go back to the experiment, check it, or ignore it. If this is really too far away, you should ignore it. If not, you should keep it and then draw the best fit accordingly. Okay? For example, look at this. 2 graphs here. What do you think? Now look at them. This one is balanced also, right? See, 2 points below, 2 points above. But then this one is too shallow, not steep enough. If you plot this, these are the 2 graphs, same graph. This one, if you plot it a little bit steep, you see, almost all the points pass through this steeper one, right? Almost pass through, and yet they are still balanced. You see, almost balanced. Therefore, this is a better one compared to this one. Okay, so this kind of thing comes from our experience. You need to do more experience and then plot the thing like this. So see, this is better. More points are closer to it, and also evenly distributed. Is it okay? Any question up to this point? I've been talking for 40 minutes.
Oh, good, sir.
Oh, good, 40 minutes. Let me see. Should I go on? Okay, just a little bit. This should be the last slide. Now, choices of axis. As I said just now, we want a linear graph. You learned it before. Linear graph means this equation. Y equals mx plus c. Okay? So from here, when you plot y against x, m is the gradient. Right? Gradient. C is the intercept. This is the simplest one, the relationship. However, most of the time we don't have such a nice relationship. For example, the one we just look at, what do we have just now? P square root m, right? This is not a linear, already slightly different. This actually is T equals something, then the mass half. So you can see that this is actually a power relationship, a power equation. X to the n. N here is half. N is the half. A is the constant. Okay, we are actually talking about this equation. So just now we plot P against square root n. But there are other ways of doing this. For example, here I show you. For power law, you can bring down the power here, the n, the index, using logarithm. Remember? Logarithm. Logarithm is the inverse of the power. So logarithm, if you remember the rule of logarithm, you take logarithm base 10 on the left. Then for multiplication, logarithm, you turn them into addition. Right? Log A base 10 plus log x to the n. But then logarithm, you bring down this power n into here, down here. Okay? Then you compare this equation now. We give a new variable, this one. You call this y. This will be your c. N will be your m. This will be your new x. See, you compare this with the linear law. Compare this with the linear law here. Compare this with the linear law, right? Y equals mx plus c. So in this way, if you choose y as your logarithm y, x the logarithm x, then the m here, this little n will be your gradient. This part here, logarithm a, will be your constant, intercept, y-intercept. Okay? So this is one way logarithm 10. But there are things like this. Look at this. This one, I think you can do that. Okay? New things like this, e. Sometimes these things appear exponential. Have you learned this function, exponential function?
Not yet.
Not yet, That's why we need to have some digress. We want to look at this new function e, and this should be the last one here. We will do here. This e here is a very important function that you will learn afterwards in mathematics. First, we start with this. This e is a new constant, just like your pi is an irrational number. We call this Euler's number, a very important mathematical function or a number. Okay, it is formally defined in this way. You see, 1 plus 1 over n power n. So you just take a limit of n equals 1, you get 2.7, I think. Then n equals 2, you get a new number. N equals 3, 4, 5, 6, 7 until infinity. Then this will converge to a number like this, 2.71828, and you never end. This is irrational. And this is the Euler's number, E. Okay? E. And this has a different form. Now, that's why it is so important. If you do something like this, 1 over 0 factorial, 1 over 1 factorial, you just sum out to infinity. As you see, right? The thing is getting smaller, smaller. So they converge into this same number. If you learn factorial, the meaning is this. N factorial means n times n minus 1, n minus 2, n minus 3 until 1. If you have 4 factorial, it means 4 times 3 times 2 times 1. So you sum up, you also get this strange number, Euler's number. Okay? And quite important, again, we can relate it to something else. Look, this equation. This equation, maybe you have not encountered up to this point, but you are going to see this all the time in the future. Especially in error analysis, for example, this will give you a complex number. You see, complex number, cosine theta I, complex number. Actually, you can draw something like this. This is a thing, the data here. This will be your cosine. This will be your cosine, and this will be your sine theta. So x and y, I will call this the complex number z, x plus I, y. Okay, and this is the component. You can write it in this way. This is also called phase. Okay, so important, this thing you will see later. You use it in signal analysis, in many other things, especially in mathematics, a lot in engineering, in circuit analysis. You also use it, two directions. You learn this in electricity magnetism later. Okay, and if you ask some people, what is the most beautiful equation in this world or you ever encountered? Now you ask mathematician this one. Many of them will tell you special cases of this, a special case of this equation. If you set theta to be pi, you replace theta by pi. You know pi is 180 degrees, right? What kind of thing you get? What is this number? E to the I pi.
-1.
Yes?
-1.
Negative different? Okay, let us try. Pi is 180 degrees, okay? What is sine 180 degrees? Sine 180 degrees, what do you get?
Zero.
Zero. So this part is gone. Yeah, correct. This part is gone. What is cosine 180 degrees?
1.
-1.
-1.
Yes, -1. You look at this equation. Some say that this is the most beautiful equations. Why? Look, 3 important quantities appears. Pi, you see this pi everywhere. E, now your new number, Euler's number appear here. And I, the complex I appear. And then the -1, a negative sign, and then 1. All the most important elements in mathematics appears here. Everything else can be set up, meaning like this. That's why people call this the most beautiful equation. And now you have seen the most beautiful equation in your life. Okay, remember this. Okay. Another thing, why is this so important? There are some physical meaning in it. Population interest. When you are dealing with finance, this number will also appear. Let's say we start with 1,000 ringgit. I want to put it in the fixed deposit. So let's say 1 year I get 3% of dividend, a bonus. Okay, 3%. The second year, this dividend plus the original principal, then you give me more money in the second year. So it compound. The interest starts to compound 1, 2, 3, 4, 5 years. Okay, and when you go to some point, and this is the result. You will analyze this. It will give you this form, this equation. That's why it is related. The Euler's number is related to interest, compound of interest. And then in science, decay, radioactive decay. If you start with 1 million radioactive atoms like plutonium or uranium, 1 million, let's say, okay. Then after some times, it will reduce to 55 half million, from 1 million to half million, and we call this half-life. Half of it is remains, the other half decays away. Okay, this is half-life, and this time taken, how rapid it decay is described by exponential function, e to the minus kx, something like this. This is the function. It will decay like this. This is the decay rate, like this. You start from 1 million. After a while, this is the time. We call this half-life. You are left with 0.5. You start from 0.5. After a while, it becomes half again. It becomes half. And this is twice of the half-life. Okay? This is the very special thing about this exponential function, half-life. The next thing is discharge of capacitor. You charge a capacitor positive, negative, right? Then you connect it with a wire. This negative charge, the electron is going to flow into the plus. So it's going to decay, goes down as time move on. And this law again is precisely this one. How the charge decay. You start from some original charge, it decay according to this law. Okay, it's like this. Sorry, this is plus x. Okay, if you plot y equals plus x, you get this. If you plot y equals exponential minus x, the one I just showed you, minus x, you flip this to the other side, you get this. Yeah, correct. This one goes down like this, exponential function. Okay, so this is the meaning of exponential function, almost time already. And logarithm, base e is the inverse of this. I think we'll talk about it this next week. I think a little bit short. Now maybe just a few seconds. Let me finish this. Okay, now this is base 10, right? Log base 10. What you do, you want to get x, you take logarithm base 10 on both sides. Okay? Log 10, 10, you get 1, you get this. Therefore, we say log is the inverse of the power. Log is the inverse function of power. Same thing here. Since now this thing here, exponential e is the number, right? 2.718, the Euler's number. You want to invert this. What do? You take logarithm base e. E is a number, 2.718. The special number, you write this logarithm, natural logarithm. Okay? So what you do is y equals ex. You take natural log on both sides. Log e. It becomes, you bring down the x, the power, log EE. Log EE is 1. You get something like this. Okay, so logarithm is the inverse of the exponential function. Natural logarithm in this case, E. Okay. Other thing, importance, you take a derivative of exponential x, you get back itself. If you take the integration of 1 over x, what do you get? Anyone?
Natural log.
Okay, you have learned this.
Yeah.
Good. Okay, now, if you do this, right, you know you get minus 1x, right, plus a c. If you do this, what do you get? You get nothing, is it? You get what? Get 0, is it? Or get 1, constant, right? Actually, you get natural logarithm. Okay, this is why these two numbers, they are so important. So I just give a crash course on exponential function. We will do some exercise next week. Important, in your calculator, sometimes you do something like this, E10, right? This E is not this E, okay? They are different. This E actually means 10 to the power 10. This is the 10 power 10, okay? It's not this E. That's why I don't like your calculator. You shouldn't. This is a bad thing. Students get confused between this E, exponential, and this E. Okay. Next week we will start doing some exercise on this, and this is the end of this class. Okay. Actually, I want to give you some activities, but too bad. Next week we'll do that. And for you, you should finish your exercise 2. Try to do that, and then look at the table. You can talk to us, and I will make a little bit modification to your thing. Okay. Thank you.
Sure.
Yes.
Could you please open the Instat one more time?
Sorry, instead. Yeah, of course. Yes.
Thank you.
Okay. Thank you very much for your time. Okay, you can go now for your next class.
Thank you very much, Mr. Teo. Have a
Thank you
nice
so
day.
much,
Bye-bye.
sir.
Thank you, sir. Thank you, sir.
Thank you. Thank you. Let me unlock your instead.
Ciao, sir.
Thank you.
Thank you, sir.
Thank you.